Mirko Dovidio is an associate professor in probability and mathematical statistics at Sapienza University of Rome. He works on the connection between stochastic processes and PDEs, time changes and boundary value problems, non-local operators, and irregular domains. We're very happy to have you here. You may please begin your talk.
Many thanks. Thanks to Pavan. Thanks to the organizer for this nice opportunity. And yes, I would like to speak about fractional boundary value problems, giving you some new results and some application. Give me. Okay. So I would like to focus on my last works, on the works of these last years, and which are listed here. And obviously, these works are works in collaboration with Bonaccorsi, with Fausto Colantoni, Pagnini, Iafrate, and Flavia Tavani. And the problem is to characterize the solution from the analytic and from the probability point of view. The solution to a problem in which we have a non-local equation, let's say, a non-local operator, but this operator appears on the boundary condition. So this is not new in case, for example, here we use Caputo-Zarbachan derivative. So in case alpha is equal to 1, we have the ordinary derivative. And this problem is not new in case you have alpha equal to 1. In particular, this problem is well known as a dynamic boundary value problem. So the problem is to consider now the red problems. Here we have the ordinary derivative. Here we have the ordinary derivative. We are looking for a function u for a given operator on a bounded domain. The bounded domain here is a smooth domain. For example, is an open connected non-empty domain with a smooth boundary. So we have to consider the trace in some sense. Obviously here, this is very simple because we are looking for a trace continuous function up to the boundary. And we have a domain, which is a smooth domain. So the trace is a sort of restriction of the function. So if you consider the trace of u, then you take the ordinary derivative of this trace, and this should satisfy this equation here for operators A and B. And so this is the dynamic boundary value problem. You can move on alpha grid in 0, 1 and consider this second problem here. Then you have a Caputo-Zarbachan derivative. I didn't mention what the Caputo-Zarbachan derivative is because I think you know very well. However, is a convolution with a singular kernel defined here. So we have the Caputo derivative here, the Caputo derivative here. Once again, we take the trace of u, we get a function b, and you have this equation here. So, so far, we have nothing actually new, because I will show you that these two problems can be treated in the same way. So if you have the same order, the same operator here and here, that is on the interior and on the boundary, but also in this case, you have the same operator on the interior and on the boundary. The problem is can be treated as a standard by following standard arguments. The novelty here is given by the blue problem. So we have something local here, an evolution equation given by the ordinary derivative. So for example, if we have the Laplacian, this is the heat equation on the interior. Then you take the trace and you get something different, which is an equation involving the Caputo derivative only on the boundary. So we have something similar to the previous talk, that is, we have something switching. We have a switching behavior, a switching process, let's say. But the problem is that we have a behavior on the interior. For example, we have a domain of dimension D, and you have a different dynamic on a lower dimensional space, which is the boundary. So, for example, dimension D-1. So the problem is to find, obviously, we have a compact domain, and we can arrive to a compact representation of the solution, for example, in L2. So the problem is to find a continuous kernel for this solution. Then our goal is to find a probabilistic representation for the solution in order to have a clear meaning about, for example, a Brownian particle moving according with this problem. So first of all, I have to introduce some notation and some objects. The main object is the sticky Brownian motion. So this is actually unusual elastic sticky Brownian motion, but this is very natural because we are dealing with Wenzel-Robin boundary condition. So we have something related to Wenzel, which is the sticky Brownian motion. So a second order condition on the boundary, the process arrive at the boundary, and if you have a pure sticky condition, the process stay there for the rest of its life. Sticky condition. Then you have a Robin boundary condition. So we have something elastic. So let me call this process elastic sticky Brownian motion. And gamma is the local time on the boundary. So we consider this measure, which is a measure given by the Lebesgue measure on the interior, and a surface measure on the boundary. With parameter here, we have eta sigma. So the sticky process has a generator given by the Laplacian with this domain you can see here. So what is important to underline here? We have function, a class of function which are continuous with the second derivative, let's say continuous. So we don't have first derivative continuous. The condition on the boundary is the second order condition. This is for sticky condition. And this is the generalized, let's say, Wenzel condition, but this part is the elastic condition. So you have something sticky described by this condition here, this operator here, and something elastic described by this condition here. Here you have the normal derivative, here you have the trace of the function. Okay, so you have some technicalities, but as I said, we are dealing with continuous function up to the boundary and with a smooth domain. So the trace is defined very, in a natural way. So the semigroup generated by G is a compact, positive, strongly continuous contraction semigroups. And obviously, if you take the limit for these parameters here, eta, for example, eta equals to 0, you may neglect of this part and you get the elastic condition. Otherwise, for sigma c, you may get only the elastic Brownian motion, the Dirichlet Brownian motion, and so on. So this is a very general definition of boundary condition. This is very well known. Some further notation, X plus. X plus is a reflecting Brownian motion. So gamma plus will be the local time on the boundary. We have a generator, which is given by G plus. Obviously, this is the domain for G plus. We denote by X dagger the Brownian motion killed upon reaching the boundary. So the killed Brownian motion. And let me focus on this point. Once we have a reflecting Brownian motion, X plus, we may write the semigroup, the Dirichlet semigroup, by considering X plus, that is the trajectory of X plus, up to the time the process hit the boundary. At that time, the process is killed. This is very well known. Okay, so this is the generator. And another things I would like to underline is that the elastic Brownian motion, so if we neglect the second order derivative, we only have the elastic Brownian motion, and the elastic Brownian motion can be written once again by considering x plus, that is the reflecting Brownian motion. This is the famous Feynman-Katz formula. And we have the reflecting Brownian motion x plus and the local time of the Brownian motion. So we are also in need of H, which is a stable subordinator, for which we have this main value here, and L, which is the generalized inverse of L. So H is a subordinator, may have jumps, and is a strictly increasing process. L is the inverse with a continuous path. Okay, the first result, this is not a result of mine, but this is well known. X may only have instantaneous reflections if and only if eta equal 0. So if you have eta equal to 0, so we have this domain for the generator, that is, we have an elastic Brownian motion. We only have the elastic condition, so the process starts from X inside the domain, move all around, hit the boundary, and instantaneously reflect. If eta is bigger than 0, the process hit the boundary and stop there for a random amount of time. The holding time is an exponential holding time. So we represent in this way the holding time. We have a collection of holding time. With the return times on the boundary, we have a sequence of holding times. And these holding times are exponential, random variable. So this is the only way, the exponential random variable, this is the only way to maintain the a semigroup. So the Markov property. The process X is a sticky Brownian motion, is a strong Markov process only inside because of the holding time. So we cannot maintain the strong Markov property. However, this condition, this second order condition, introduces, as I said, the exponential holding time, and we say that we have slow reflection on the boundary. So the process stopped for a while on the boundary, which is an exponential holding time, and in the literature, this is termed slow reflection. So the process reflects, but slowly. Then if we consider this problem here, this is for alpha between 0, 1 or for alpha equal to 1. So this represents the two problems I gave you in the first slide. And this problem can be treated in a very simple way. Indeed, if you have A, which is the Laplacian, B, which is the elastic part, let's say, under the condition that the Laplacian is continuous up to the boundary, then I can replace, let's say, since we have the Caputo derivative, we have this equation on the interior. But since the Laplacian is continuous up to the boundary, I can replace here the Caputo derivative with the Laplacian. So in a certain sense, let me, roughly speaking, this is the main reason why we have the generator G, that is the generator of the elastic sticky Brownian motion. So this problem here can be treated in this way, which is a very standard way, that is the fractional Cauchy problem. We have a generator of a Markov process. We have something fractional here, the Caputo derivative. So this is a fractional Cauchy problem. The probabilistic solution of this problem can be written in terms of the time change with respect to L, which is an inverse to a stable subordinator over the alpha. So this is very standard. And also in this case, we may apply this standard theory. And the main reason is that basically you may consider an operator matrix on the space of continuous function. That is, we may consider this problem here. Once you have defined U with the trace, then you have this Cauchy problem here. So if you consider the red problems I have presented before, then these problems are not, we have nothing new, let's say, because we may treat this problem as a fractional Cauchy problem. So we may consider the time change, as you know, with respect to an inverse to a stable subordinator, as it is well known. So some further information about this problem. And so we have X time changed with an inverse to a stable subordinator. So we may define the lambda potential in this way, and you get something related to this ratio here. So this is the lambda potential associated to this problem. This solution can be written in this way by considering the density of L. This is the semigroup of X, written here, of the sticky Brownian motion. And what I would like to underline here is that in general, when you consider the time change L, so when you consider this object here, a Markov process time changed with an inverse to a stable subordinator, you may consider the exit time or the occupation measure, and by just noticing the red line that is from the lambda potential, let us consider this object here, which is related to the exit time from the set lambda of the domain. So because of this ratio here, alpha is between 0 and 1. So if you take the limit as lambda goes to 0, you get here, you can see here, you get the mean exit time for lambda, which is infinite. And this is true for all subset of the domain. So for this reason, we say that the process is delayed. So if you consider this time change, the process is delayed. And the process may spend infinite mean amount of time in order to exit from small subset of the domain. Now we introduce we say something about the fractional boundary value problem. So I speak about fractional initial value problem in case of fractional Cauchy problem, the problem I have introduced so far. Now I am speaking about the fractional boundary value problem. So you have something fractional only on the boundary. The blue problem I have introduced before. So for this problem, I am able to show that we have a continuous solution. Okay, the solution should maintain some property. Let me skip some technicalities. However, the fractional derivative should be well defined for the trace of the solution. So, however, you can write the solution, which is continuous, in this way, by considering this probabilistic representation given in terms of X bar. And X bar is a process obtained by considering the reflecting Brownian motion time changed with this time here, random time here. So you may neglect of this part, the exponential. This is only given by the elastic part, okay? If you only consider, for example, the elastic coefficient C equal to 0, so you only have a reflection, the Neumann condition. So in order to understand what is going on, we may focus on this object here, X plus, which is the reflecting Brownian motion, so the process arrives at the boundary. And when the process arrives to the boundary, we have to take into account this random time here, which is the inverse of this process here. So you have T plus the stable subordinator with a random time given by, apart from the constant, given by the local time of the reflecting Brownian motion. So when the X plus hit the boundary, the local time increases. This means that H jumps. If H jumps, so V bar jumps, the inverse process has a plateau. And for this reason, this process here is forced to stay on the boundary for a random amount of time. And this random amount of time depends on H, which is independent from the process, and on the local time The local time introduces the exponential holding time I have introduced before. So we have a couple of two mechanisms, competitive mechanisms, let's say. Here you have something related to the local time, so something related to the process. Here you have something independent from the process. So the process stopped for a while on the boundary, and for an independent reason, okay? That is for the process H, which is independent from the process. So as I will say in the next slide, this holding time may be associated with something different from the process. In particular, it could be associated with the boundary. Okay, so the next result, as I said, we have a compact representation, and we can show that also in this case, for the non-local dynamic boundary value problem, we have a continuous kernel for the compact representation on L2. The last result, theorem 3, we have a sequence of holding times. So as I said before, for the sticky process X, the holding times are given by a sequence of exponential random variables. Here, we have a sequence of holding times, which are given by Mehta-Gleffler random variables. If alpha goes to 1, we obtain once again the exponential. So the holding time now are Mehta-Gleffler random variable, no more exponential. In particular, we have that X bar start from X on the interior, move like a Brownian motion, hit the boundary, and stop there for a random amount of time given by the Mehta-Gleffler random variable. Then, after this time, it starts afresh like a Brownian motion, according with the Laplacian. Okay, there is a nice proof of this. Obviously, my aim is not to give you the proof, but I would like to notice this important fact that X bar is the process associated to the non-local dynamic boundary condition. If you take alpha equal to 1, you get X, which is the sticky Brownian motion. And we are able to consider, starting from the probabilistic representation of the solution associated to X bar, we are able to consider to introduce a semigroup S lambda t, which is associated to the Laplacian with this domain. So we arrive at this new boundary condition, which is the boundary condition for a process depending on lambda. Lambda is, for example, if you consider the lambda potential, you somehow arrive after some calculation to this domain here. And the speed measure for this new process is given here by this ratio here, by including this ratio on the speed measure of the process X. If alpha is equal to 1, obviously we get rid of lambda and we get X. However, the holding time here are given by Mehta-Gleffler random variable. And we say that we have slow reflection depending on the exponential holding time of the process. So there is a time depending on the process, which is exponential for which X bar stay on the boundary. But there is an extra time, which is given by the independent subordinator. For this reason, we get the Mehta-Gleffler holding time. So you have a delayed slow reflection. So we have a delay for the slow reflection of the process. And this introduced some new information about occupation measure. So we are able to introduce the occupation measure, okay? We can say that the occupation measure can be bounded by the exit time from a subset of the domain. Then we can study just in order to have in order to proceed with a rough discussion, let's say, we can discuss only on exit time. And the exit time can be obtained, as I said before, by considering the potential with lambda, which goes to 0. In particular, we define the potential, the lambda potential, which is, let's say, the Laplace transform of the solution, for this function here, that is including lambda as a subset of the interior. And you have this representation here for this object, in which you have the local time of the reflecting Brownian motion and the reflecting Brownian motion. Then you can introduce this lambda potential for lambda as a subset of the boundary. And here you have this ratio here. Once again, you have the local time of the reflecting Brownian motion and the reflecting Brownian motion. Here you have a path integral representation. So since we are considering only a subset of the boundary, you have to consider only the time the process spent on the boundary. So we arrive at this path integral representation. What is interesting is that because of this ratio here, if you consider the mean time the process spent in order to exit from a subset of the interior is finite for all values of alpha. If you consider a subset of the boundary, then you consider the time the process spent in order to get off of this subset. Then you have this mean time is finite only if alpha is equal to 1. Otherwise, you have something which is infinite. So the process can be trapped in a subset of the boundary. Obviously, this is a notion given in mean. There is maybe we may have some time, some finite time for some path for which the process get off of lambda, but in mean you have something which is infinite. So you may associate this property, this fact, with a notion which is a notion for the boundary, okay? So maybe there is something on the boundary which can be associated with this fact. And in particular, we can I can give you the first application to this problem. So non-local dynamic boundary condition. We have holding times on the boundary, and the mean holding time the process spent on the boundary is infinite. So the process can be trapped on the boundary. So as I said, I have introduced this process for smooth domain. Here we have something different from smooth. For example, we have here a Koch domain, so a Lipschitz domain. You take the limit step by step. You construct the fractal, you take the limit, and you get the fractal as a limit. So this is a first step in the construction, is a Lipschitz domain. If you take the limit, you get the Koch domain. Example are given by these pictures here. So you have a square, and for example, here, you have in this triangle, you have a Koch curve, okay? Put this curve in each side, and you get this Koch domain. Here you have a square, but you put the Koch curve outside in each side, and you get this domain. So this domain and this domain are fractals, if you take the limit. And in particular, this domain are irregular, but this domain are not so irregular. Indeed, we have a definition for trapped domain, and these domains are non-trapped. That is, if I consider the reflection on the boundary here, the process is not trapped on the boundary. If you have a Neumann condition, the process is not trapped. You can follow here the definition given by Burzic and Marshall. And in order to obtain a trapped domain, we have to move on this modified Koch domain. So you put some window here. And depending on the wall, obviously, we have different situation. We have a result associated with the order alpha of the Caputo derivative, which regulates the openings here of this window. And depending on alpha, we have trap or non-trap domain. That is, depending on this window, if you take the limit, so step by step, you construct the Koch curve in its sides, and you take the limit, you get a fractal. This fractal is a trap domain for the Brownian motion. That is, if you go ahead here in this boundary, you have very, very small triangles. And in that triangles, you have a fractal. And the Brownian motion can be trapped there for some time. So this is trap, this is non-trap. So you may consider the fractal constructed here as a domain for X bar. So you have an irregular process on a regular domain. And you may consider X plus, which is, let's say, a regular process, a reflecting Brownian motion, on the irregular domain here. If you look from a distance, you see the same story. That is, you can see a Brownian particle which is moving here and is trapped somehow in some region of the boundary, and then this particle, let's say this material point, starts afresh moving inside. But if you look here you have the same story, but now the holding time on the boundary depends not on the boundary, but on X bar, because of the time change I have introduced before. So this is a first application, and here we need the Lipschitz domain, not smooth domain. We are able to produce this theoretical result because there are many results in the literature we may consider and apply here in order to say, in order to get the same theorems I gave you before for Lipschitz domain, not for smooth domain. However, if you want to focus on smooth domain because they are simple object, then you once again consider this. Take the limit, you get the fractal, which is trap for the Brownian motion. If you consider here a blue line, which is a smooth line, okay, all around, step by step, you have different Koch curve. And once again, you consider here the smooth line, okay? So the smooth line, let's say, somehow neglects the rough part of the boundary. So if you take the limit, you have the Koch, you have the fractal outside, and you have something smooth inside. Then you may apply the result I have presented so far. That is, I can say the process X bar is an irregular process moving on the smooth domain. And X plus is the regular process moving on the irregular domain. So this is our first application. And when we consider this approximation, obviously we consider a distance less than a small value. And we are able to proceed in this way. Obviously, the result is that we can produce this smooth line only up to a certain point. After that, we have to neglect the rough part of the boundary. Okay, this is a first application. After that, since we are considering holding time on the boundary, so the definition of holding time, this is an holding time in the sense that X is on the boundary. So the process started on the boundary, stay there for this random amount of time. Indeed, at this random amount of time, the process is inside the domain, is in the interior, because lambda is a subset of the interior. So this is the definition of holding time, and we say that, in words, we say that we have no excursion of X on the interior under this random time. No excursions means that you have zero Poissonian events. We may say something like this. This is very standard in excursion theory, but we can do the same for X bar. So this is the definition of holding time, no excursion of X bar on the interior. So we have something which is a Poisson process, no Poissonian event. In particular, N is the Poisson process, which is density, and N bar is the fractional Poisson process. So if zero Poissonian events are given by the exponential law, as I said, for X, that is the sticky Brownian motion, for X bar, we have N bar and Mehta-Gleffler distribution. So we can see the story by considering the excursion theory. And starting from this, we can discuss about the boundary trace process. Actually, I have no result on the boundary trace process, but I have result on a process which can be associated to a boundary process. So the boundary trace process can be written in this way. So you have x, the local time of x, take the inverse. So you consider x only for the time for which x is on the boundary. And this is the boundary trace process for x. In a similar way, you may define the boundary trace process for x bar. Remember that x bar is a strong Markov process on the interior because it looks like x, behaves like x. It's different only from the boundary because of the holding time. And is also non-Markov, obviously. So, okay, this is the definition for boundary trace processes. Now we assume that, now we introduce the return times for x plus on the boundary. So a sequence of random times for x plus. And we may consider this process here, which is a process on the boundary, given by the composition of x plus with this object here, which leads to this composition here. So you have x plus at the time the process arrives at the boundary with the time given by nt. So you have tau1, tau2, tau3, and so on. So the process is on the boundary, and we jump in all the points on the boundary, the reflecting Brownian motion, where the reflecting Brownian motion has arrived along its path. The same for x bar. So we may define, this is the same story, we have the reflecting Brownian motion at the time the process is on the boundary, and we have the first, the second, and so on. But what is changing here? So in order to jump from one to another point, here you have to stop there for an exponential holding time. Here we have a Mehta-Glefler holding time because n bar is a fractional Brownian motion. So we have a process on the boundary, and the process is on the boundary and jump to another point on the boundary according to an holding time. Here we have exponential holding time. Here we have Mehta-Glefler holding time. These processes are not boundary trace processes because we have some different technical situation to well organized, but I would like to underline that we have this situation here. So for the boundary trace process, it is well known that we have the Dirichlet-Neumann operator. If you are able, which is an operator, this is well known. Okay, I will like to skip the definition because of the time. And this is the generator of the boundary trace process, which is a Markov process in case of X. In general, for these processes on the boundary, I have defined in the previous slide, we may define a process, a generator like this. So if you have this generator, this is, I have no calculation so far, but I think this is very simple because I have a composition with the Poisson process. However, if we have this operator here for X, so you have the process X on the boundary, then we are able to consider the composition with L. So the same process for X bar. And we are able to consider this equation here involving the Caputo derivative with respect to time for the process X bar on the boundary. So this is a fractional initial value problem. So the boundary, as I said, is a compact manifold. We assume that is a compact manifold without boundary. Okay, so this is a standard theory from the fractional Cauchy problem, and we obtain this relation between the standard and the fractional Cauchy problem. Okay, so we said something about the bounded domain omega, but we have a result also on the real line and also application for the one-dimensional case. So this is actually the same story as before. If you consider, instead of omega, which is a bounded domain of dimension d, we consider the half line, we have this problem here. So we have here the first derivative in place of the normal derivative. the heat equation, and so on. The probabilistic representation, we have the same probabilistic representation, so it's based on the reflecting Brownian motion on zero infinity, and this process here, which is given by this process here. So h, time changed, apart from the constant, time changed with the local time of x plus. Obviously, the measure we are interested in now is a Dirac measure, because the boundary is now given by the only point 0. Here, things are simple, and we can write the solution explicitly. We have the potential written in this way. This is the resolvent for the Dirichlet problem, for the Dirichlet Laplacian, let's say, the killed Brownian motion. We have this part, including F0 and so on. So this is very explicit. And starting from this, we are able to arrive to another useful application, useful in my view, obviously. And if you have a diffusion on zero infinity, then we may start discussing on the networks, on graph. So we tried to find a solution for the star graph. So we have a metric graph, which is defined thanks to Mugnolo as a collection of afflines. Okay, you have a collection of affline. Here I draw a collection of bounded interval, let's say. But the fact is that we can associate each edge of this star graph with a bounded interval of the real line. So we may consider the Brownian motion on the star graph as a collection of Brownian motion on real lines. So the process X calligraphic bar, in order to record the dynamic non-local problem, is the Brownian motion moving here on this graph, on this star graph. This is the associated problem. We have the heat equation. This is the Laplacian on the graph. This is very simple. It's defined in a very simple, useful way. This is the Caputo derivative. This is the Kirchhoff condition. So we have the weights here, the probability to stay in a different edge. And the weight obviously satisfy this condition. And alpha belongs to 0 and 1, also 1. So if eta is 0, you have only Kirchhoff condition. If you have uniform distribution for these probabilities here, we arrive to the standard Brownian motion, because we have Brownian motion on the star graph. If eta is different from 0, we have a fractional boundary value problem associated with x bar on each edge. So in particular, we have a Brownian motion moving on a given edge, arrive at the vertex, and stop there for a Mehta-Gleffler random time. Then decide, according to these probabilities here, or according to this process here, theta, decide in which direction the process has to go, and after that, start afresh as a Brownian motion. So we have Mehta-Gleffler holding time on the vertex. So the process can be written as a edge selector and x bar. The edge selector satisfies this identity here, gives the probability to go in a given edge. And so we have a Brownian motion on a metric graph and Brownian motion on networks, because we can collect. Here we have collected affline, let's say. So we have star graph. We can collect star graph and we get a networks. So applications. For the fractional Brownian motion on RD, we can consider interactive particle systems. For example, you have in the one dimension, this is the path of the Brownian motion. The Brownian motion is sticky at 0 and is sticky for a random amount of time. I have considered Caputo-Zarbashan derivative, but so we have Mehta-Gleffler random variable, but Mehta-Gleffler holding time. But if you consider general operators, then you may consider general holding time here. Then the process starts afresh as a Brownian motion. So this is the sticky Brownian motion x bar. If the sticky Brownian motion is given by this distance here, the distance between these two paths, so distance 0 means that these two paths are the same. So this is the situation in which two particles move separately, then they collide and collapse and start moving together as a unique particle. So this is a very nice application for the interactive particle system. So we can manage this part of the trajectory. This is the holding time. Further application can be given in finance, for example, model of sticky expectation. So the investor update their beliefs too slowly. So in general, also for the bank interest rates, we have a slow reaction. In case you have a slow reaction to something, you may speak about sticky behavior. If you consider fractional Brownian motion, fractional boundary value problems on networks, you may, obviously, this is very clear. You can describe traffic models. So I don't know, data or a car is moving, then arrive at a node, at a vertex, stop there for some reason, which is random, which is independent from the car, from the data, and so on, and then start again. And I have also further application for the earthquake models, but because of the time, I decided to skip this part. And I think also fractional boundary value problems are useful in a very general setting. I tried to give you an idea of this by discussing the connection with the stochastic resetting very quickly because of the time, but this nonlocal boundary value problem can be associated to the stochastic resetting. In a way, I will show you. Let me consider the elastic drifted Brownian motion. So you have this generator here. Obviously, the drift could be 0. And this domain here. So you have an elastic condition. The process arrives at 0 and reflect. The process is killed up to the elastic kill given by the exponential random variable. Okay, so we have now the generalized Caputo derivative. So we have a general kernel, let's say, and our first result is that if you consider this problem here, this is very well known. So this is the Cauchy problem for the elastic drifted Brownian motion. The only difference is that we consider constant initial datum. So the initial datum is 1. So we have a solution. This is very well known. We are able to find a solution. The result is that this solution coincides with the solution here, where we have a non-local boundary, dynamic boundary condition here, where this generalized Caputo derivative is characterized by this Bernstein function here. And this Bernstein function could be this one or this one. So in particular, it could be associated to subordinators. Then let me say something about the second theorem. If you consider a process started from X and arrive at 0. So the time the process spent from X to 0 is a variable which equals in distribution a subordinator, which is a tempered subordinator with a symbol here, if the drift is negative. Equals in law a killed tempered subordinator with a symbol here, if the drift is positive. In the same way, we can introduce the last theorem, that is, we can consider the inverse to these subordinators, and we arrive at the local time of the elastic drifted Brownian motion at 0. So the local time equals in law the inverse to h, or the inverse to h minimum the exponential random variable of parameter mu. So in particular, we are able to characterize the time the process spent from a given starting point to arrive at 0. And from this, we also characterize the local time at 0. Then, now I introduce for the first time the Marshall type derivative. It's written in this way. And I also introduce for the first time a non-local boundary value problem, which is not dynamic. Now, non-locality is in space. So this is a generalization of a well-known work by Ito and McKean, but also by Feller. And a generalization in case you have a convolution, we have an operator written in this way, where this function here is a kernel, a singular kernel. Because in the works by Feller, Ito, and McKean, this measure here is a measure with density, and the density is non-singular. But we are able to generalize this fact to put here a Marshall type derivative. And what we obtain is a representation in terms of the elastic drifted Brownian motion plus an additive part, which is a jump. This jump is constantly 0, except in case this process hits the boundary point 0. So this jump depends on the local time. So these are an example of trajectories. So the process starts from x, the drift is negative, arrive at 0. Then this jump push away from 0 the path, and the process starts afresh as an elastic drifted Brownian motion, and so on. So this is the process associated to the first picture. If you consider the time reverse process, so you fix a window of time, and you consider the time capital T, then you consider this path here, not from 0 ahead, but in the opposite direction. So you arrive at this path here. And putting all together, you have the time reverse process. That is, the process starts from here, arrive at a given point, and the process is pushed, is stochastically resetted at 0. Then the process starts afresh as an elastic drifted Brownian motion. At a certain point, the process is pushed at 0, is stochastically resetted, and so on. So this is a special case, very simple case, which could be associated with a well-known stochastic resetting, which is the first passage time resetting. But this problem here can be associated with any general stochastic resetting. Also in case we do not have a drift, also in case we have a path, a standard path of the Brownian motion. So this cannot be associated with the first passage time resetting. And so the message here is that the non-local boundary condition like this can provide a useful way to characterize all the stochastic resetting we are interested in. Managing the jumps, managing the time the process spends in order to get a reset, and so on. And just a conclusion of the discussion of this picture, let me observe that if we start from x with negative drift, the time for the process to arrive at 0 coincide with the time the process spends starting from 0 with positive drift in order to arrive at x. That is, the time the process spends from here to here is the same the process spent from here to here. This is the key point. Okay, so let me let me show you some references. These are references for the fractional Cauchy problem. So most part of these references are very well known, and these references are related with the fractional initial value problem. So this topic has a long history. A lot of researchers studied this topic, and basically we have the fractional Cauchy problem. And here we have some references associated with the dynamical boundary value problem For example, this paper here, the first one for the case alpha equal to 1. So there is no literature in case of no local boundary condition. So for alpha between 0 and 1. From Burzi, Chen, and Marshall, this is the paper I already mentioned about the trap domain. Goldstein for the derivation of physical interpretation for this kind of derivative, that is in terms of energy spent by the particle and so on, or in terms of physics from the bulk and from the surfaces. And Benzel is the very well-known work for the Benzel and Ito, McKean, and Feller, 5, 8, and 13. The works dealing with the second order boundary condition, that is for the sticky boundary condition. Okay, I think I can stop here. Many thanks for your attention.
Thank you very much, Professor. The video, that was actually very nice. So I see that Professor Scalas has a raised hand. Please go ahead, Professor Scalas.
Thank you very much. Can you hear me?
Yes,
Yeah.
loud and clear.
Very good. So hi to everyone, and thank you very much for this very interesting afternoon. So I would like to ask you if in 1 or 2 minutes you can summarize the application to earthquakes that you mentioned when you were discussing applications.
Yeah. Okay, this is I tried to say something, but this is not so easy without a slide. But basically, the fact is that for the earthquake, you can, first of all, we have a region. In this region, you can select some direction. So this direction can be described by edges. So you have a graph. And obviously, you can characterize, so this part here. So you have edges characterizing all the directions in a region. And the differences are given by the different, for example, if you have a direction in which you have rocks, in another direction you have sand, another direction you have water, or in some other direction you have a mix of this. So you have you can characterize this situation in terms of edges and in terms of this probability here. So it's very simple. You have to go in this direction, you have high probability for this. It's not so simple, you have a low probability for this. Okay, after that, you have a motion moving on this, and this motion is not the earthquake. The earthquake is something which can be described by the Brownian motion, but the Brownian motion does not describe the earthquake in the sense that, for example, the time you have here a star graph. If you collect more star graph, this means that the earthquake goes from the main event to the second event, from a vertex to another vertex. So from a star graph to another star graph. And you have a Brownian motion characterizing the time the earthquake span to go from a vertex to another vertex. So to leave a star graph and arrive to another star graph. So a Brownian motion, the first Brownian motion, is useful to characterize this situation. Then you have another Brownian motion, which is a Brownian motion characterizing only the situation on the vertex. So here you have this equation. So the process on the graph stops for a while on the vertex. The holding time is independent, because it's related to another Brownian motion, which is completely different. And this other Brownian motion gives the accumulation of energy. For example, you have a situation like this. So the Brownian motion is a Brownian motion with drift. So the drift characterizes the vertex, that is characterized the region, for example. And the Brownian motion arrives at a certain level, Then we have the rupture. So this is the maximum level of stress. And here you have an earthquake. So if you have here, you are in the third vertex, the third star graph. You have accumulation energy. After that, according with this energy, you have a rupture. And the new process, the other Brownian motion starts and go on a given edge. Then arrive to the other vertex, and you have the second Brownian motion on the second vertex with another accumulation energy depending on that region. So I hope, I'm not sure to provide a clear description, but this is the situation.
No, you gave an idea, which was what I needed somehow. So you have a phenomenological model, which is sort of driven by the physics of the phenomenon. So it's a step further from purely statistical models, like spatial-temporal models, without a relationship with the physical mechanisms that...
No, there is a connection. There is a connection.
Yeah. No, but you have a connection. This is what I was saying.
Yeah.
Whereas in other statistical models, there is no connection.
Okay. Because our work is based on a previous work in which this connection with Brownian motion was already studied, but not in this way, not in terms of graphs, not in terms of non-local boundary conditions, but there are many functional of the Brownian motion which are useful to describe situation of the earthquakes.
Thank you very much.
All right. Are there any more questions? Please raise your hands. I don't see any raised hands. So is there any final comment or remark? Probably no. So this is a good point to close here. Thank you very much, Professor Dovidio, for this wonderful talk. It's been a pleasure to have you here.
It was a pleasure for me too. Thank you. Thank you very much.
The pleasure was ours. Thank you.